Next we have number 16, where we have to show that the Goldbach conjecture, we will recall what this is, implies the following, that for any even integer 2n, in this context it means even positive integer. There exist positive integers n1 and n2 such that 2n equals the sum of their 5 values. The case where n is 1 is very easy, because in that case 2n is just 2 and 2 is phi of 1 plus phi of 1. So we can assume that n is greater than 1. That means n is at least 2. So 2 times n plus 1 will be greater than 4. Actually, if n is 2, then how much is it? 2 times 3, that is 6. And that is why by Goldbach's conjecture, there exist odd primes p and q such that 2 times n plus 1 is the sum of those odd primes. Actually, this conjecture, it's more general formulation, the formulation that is more general than what originally Goldbach stated is that any even positive integer greater than 4 is a sum of 2 odd primes. But then if 2n plus 1 is p plus q, then what is 2n? 2n is p plus q minus 2, or which can also be written like this, p minus 1 plus q minus 1. P minus 1 is phi of p, q minus 1 is phi of q, because p and q are odd primes. So that's how you have expressed 2n as a sum of two phi values of some positive integers, p and q. Next we have number 18, where we have to find all the solutions of these two equations. The first one is phi of n equals 16 and the second one is phi of n equals 24. So we consider this equation first. Let n be a positive integer for which this is true. Now if p is a prime divisor of our integer n, then by exercise 13, phi of p is a prime divisor of phi of n. That means p minus 1 divides 16. So from this you get an idea of what the prime divisors of n are, possibly. And these are 2, 3, 5 and 17. These are the possible p's for which p minus 1 divides 16. Now consider any integer k at least 2, and you take this value phi of 3 to the power k. Using the usual phi formula, that turns out to be 3 to the power k minus 1 times 2, because this times 1 minus 1 divided by 3, which turns out to be this. But this of course does not divide 16, because there will be some positive exponent here. So 3 is available here, and 3 of course does not divide 16. But what is 16? 16 is phi of n. So for such a k, phi of 3 to the power k does not divide phi of n. So by exercise 13, 3 to the power k cannot divide n, because what that exercise says is that if this divides this, then this has to divide this, but this is not possible. And that is why if 3 to the power l divides n for some non-negative integer l, then l can be either 0 or 1. Not more than that, not like k. Similarly for the primes 5 and 17, the same conclusion can also be drawn for these primes. So taking everything into account, this is how n looks. This is the general structure of n, where these exponents in general are non-negative, especially a is some non-negative integer, but b, c and d further have to belong to this set, which of course comes from this situation, and also this line that similar conclusions can be drawn for the primes 5 and 17. Now we have to look at cases, depending on what this b, c and d can possibly be. Actually, we have to see only two cases depending on whether b is 0 or 1, but under each case there are subcases. Let's first consider b to be 0. Then 16, which is phi of n, becomes this. Phi is multiplicative, don't forget that, and these individual prime powers are mutually co-prime, relatively prime. So that's why phi distributes over this product, and because b is 0, this thing is not there. So now we are going to consider subcases depending on what c and d are. To make things easier to follow, I will keep some gaps between subcases. This is say the first one, where C and D are both 0. Don't forget that each one of them can be either 0 or 1, but still there will be a few subcases depending on which one is what. So if C and D are both 0, then this is 1, this is 1. Phi of 1 is just 1. So this equation reduces to this. 16 equals phi of 2 to the power a. Phi of 2 to the power a is 2 to the power a minus 1. So from this simple equation you find that a is 5. So a is 5, C is 0, D is 0 and B anyway is 0. So that means n is just 2 to the power 5 or 32. So this is one possible number for which the phi value is 16. Now we are going to see others. Next, let's consider the subcase where C is 0 and D is 1. Then 16 becomes phi of 2 to the power a times phi of 17. 17 is prime, so its phi value is 1 less than the value, that means 16. After cancelling 16 from both sides, you get this. Now, there are two numbers whose phi values are equal to 1 and 2, and accordingly we get these two possibilities. When a is 0, this power is 1, and when a is 1, this power is 2. But then what's the corresponding values of n? If a is 0, then we only have 17. So that's why that is one value. Whereas if a is 1, 17 is always there because d is 1. But if a is 1, then we have additional 2. So 2 times 17 is 34. In the next subcase, C is 1 and D is 0. C is 1 means 5 is there, and D is 0 means 17 is not there. So 16 now becomes this. Phi of 5 is 4, so 4 times this. After cancelling 4 from both sides, this is what you get. And solving this equation, you can clearly see that a has to be 3. So now what are we getting? A is 3 and there is 5 and nothing else. 3 and 17 are not there. So that means the cube of 2 is 8. 8 times 5 is 40. So this is another n value. And then the final subcase where C and D are both 1. But then what happens to our equation? 16 equals phi of 2 to the power a times phi of 5 times phi of 17. Both of these will now be present. So the right hand side becomes 4 times 16. But then after cancelling 16 from both sides, if you solve for this, you get this fraction, which of course is absurd because this is an integer. And that is why this case itself does not arise. I am calling it a case. I did not write subcase because we did not call the original one a case. You can write anything you want, okay? The mathematical content is what matters. So that means this is not possible and we are not going to get any value of n from this. Then comes the next case where b is 1. So this time 3 is there, okay, and its exponent is 1. So if we now go back to our original equation, that will be this. Phi of 3 will be 2, which after cancellation leaves you with an 8 on the left hand side, and the right hand side is just this. And now under this case also 4 subcases will come. So the first case, C and D are both 0. So now the equation reduces to this. 8 equals phi of 2 to the power a, which is 2 to the power a minus 1. And then solving this, you get a equal to 4. So a is 4, and because b is 1, so 3 is there, and 5 and 17 are not there because c and d are 0. 2 to the power 4 is 16. 16 times 3 is 48. So this is another value. Next, let C be 0 and D be 1. So this time 5 is not there, but 17 is there. And phi of 17 is 16. So here you immediately sense that something is going to go wrong. And yes, something goes wrong because after cancellation, this is what we get. 1 divided by 2 equals phi of 2 to the power a, which is not possible. So this case does not arise. Next case, C is 1 and D is 0. So our equation reduces to this. 8 equals phi of 2 to the power a times phi of 5. So now 17 is not there. And this time nothing goes wrong. Phi of 5 is 4. So after cancellation, this is what you get. From which it follows that a needs to be 2, because this will be 1/2 of the input. It's a power of 2. So if you have 4 here, then you should get 2. You should get 2 means then only you get 2. So that's why a needs to be 2. But then what happens to n? A is 2 means what? You have 4 in our number n. Along with that, you also have 3 and you also have 5. 3 times 5 is 15, 15 times 4 is 60. And finally, the subcase where C and D are both 1. And in this case, things go wrong. 8 equals this. So now 5 and 17 are both there, which become 4 and 16 because their 5 values are being considered. And then after doing cancellation, this is what you get, which of course is not possible. For the second equation, phi of n equal to 24, one can similarly show this. This is how the general n would look. 2 to the power a times 3 to the power b times 5 to the power c times 7 to the power d times 13 to the power e, where now a and b are some non-negative integers and c, d and e need to be from this set. That is, each one of them is either 0 or 1. And so this part is left to you, and let me give you what the n values are that you will finally get. These are the solutions: 35, 39, 45, 52, 56, 70, 72, 78, 84 and 90. And finally, let's also see number 20, where p is some prime and k is some positive integer which is at least 2. Then we have to show the following equation is true. Phi of p to the power k equals p to the power k minus 2 times phi of p minus 1 whole square. We start the solution by simply considering the left hand side, and then we start to calculate. Phi of p to the power k is p to the power k minus 1 times p minus 1, and then we can distribute phi over this product because this and this are co-prime, they are relatively prime. Then similarly, this one is p to the power k minus 2 times p minus 1. Note that in order to have these calculations, we need k to be at least 2. And we keep this one as it is. But then in the last step, you go back and see what exercise 10 tells you. It tells you that phi of n squared is n times phi of n for any positive integer n. So from there, p minus 1 times phi of p minus 1 becomes phi of p minus 1 whole square. So that's the solution.